Okay, the example we want to look at right now is a ball is dropped from an 828 meter tall building. Its position t seconds after being dropped is this. S of t equals 828 minus 4.9 t squared meters above the ground. And it's known that it will hit the ground at approximately 12.999 seconds. And the question is, what is its velocity when it does hit the ground? So its height looks generally like this, where when it's dropped from 828, then at 12.999, it's going to be at height 0. And so we can think of a point maybe a little bit further away, 12.999 plus h. And if we found the average rate of change between these 2 points, it would give us an idea of what the velocity or the instantaneous rate of change at 12.999 would be, especially if we let h here go to 0. In other words, if we let this point get closer and closer to 12.999. So I'm just taking the average rate of change between those 2 points, and we're going to take the limit as that h goes to 0, and then that should give us the instantaneous rate of change right at 12.999. So the error that we ran into in class was I wasn't taking enough decimal places, and I thought 3 decimal places was enough, and in some places I took 4, but as you're working through this problem, it just turns out it's not enough. So what we're going to do is we're going to take a more general approach. Instead of at time 12.999, we're going to say that t equals a, some generic time a. And we're going to solve this problem, and then at the end we'll plug in 12.999. So time equals a seconds. This will allow us to not have to worry about decimal places, and we'll still be able to solve the problem, but in a more general way where we could actually find out what the velocity not only is at 12.999, but at t equals 5 or t equals 8 or t equals 10. We could find the velocity of that ball at any point. So this is the problem that we're going to solve, and we're going to use this formula to do it here. And so we've got the limit as h goes to 0 of s of a plus h, and that will be 828 minus 4.9 times a plus h squared, just putting in a plus h as an input into this function here for t. We'll do the same thing over here. We're going to put as an input into the function s of t, we'll use a for t. That's our input value. So now we have minus 828 minus 4.9, not t squared, but a squared, because that's our input. And on in the denominator, a plus h minus 8 turns into h. Okay, so we're just going to clean up all of this stuff right here, and things drop out pretty nicely. We still have the limit as h goes to 0. We can't plug in 0 for h because it would create a 0 in the denominator, which we just can't do. But we've got 828 minus 4.9 times a squared plus 2ah plus h squared. All of this just came from this right here, where that's really a plus h times a plus h, and if we multiplied all of that out, we would get this expression right here. Minus, I'll distribute the minus 828 minus minus, so a plus 4.9 a squared, all over h still. And then one last distributing, getting rid of parentheses, we have 828 minus 4.9 a squared minus 9.8 ah minus 4.9 h squared. All of that just came from taking this guy and distributing him through these terms in the parentheses. Minus 828 plus 4.9 a squared all over h. And you've already seen probably that a lot of these are going to drop out. 828 minus 828 minus 4.9a squared plus 4.9a squared. We're left with just these guys and an h in the denominator. And that's kind of nice, whoops, because we're going to see that that h in the denominator will go away. Both of these terms have an h in them, so I'm going to factor that towards the front. So h times negative 9.8a minus 4.9h all over h. And here's where the beauty happens. H gets to cancel with the h in the denominator. And finally, we don't have to worry about a limit anymore because we can, this guy's gone. We can just take h, and wherever there's an h, we can put a 0 in for it. So this will equal negative 9.8a minus 4.9 times 0, which becomes just 0 itself. And so in the end, the instantaneous velocity at time t equals a seconds will equal negative 9.8. And the unit on this is meters per second. The reason I know that is because the numerator was all about meters, that was calculating height, and the denominator was all about seconds, that was calculating, counting time. So the end result should be meters per second, and it is negative 9.8 a, whoops, there's an a here, 9.8 a meters per second. The a is still right there. So this is the velocity at any time a for that object. We're assuming there's no air resistance because in reality air resistance is going to slow that guy down, but we'll say this is a world where there is no air resistance, and so the last thing we want to do is find out at 12.99 seconds what is the velocity, remembering that all of this is the velocity of the ball. So negative 9.8 times 12.999 meters per second, and that is negative 1248.42 meters per second. This is the velocity of the ball when it hits the ground at 12.999 seconds, and that's assuming no air resistance at all. That's pretty fast. That's super duper fast. And so in class we ran into some problems. This is actually an approximate, it's not an exact number, and so it was not yielding the correct answer in the end. So this is a good general way to solve this problem, because if we just keep some generic t equals a, we don't have to worry about any decimals along the way, and then we get an answer where we could literally find the velocity for any time a.